Dream to become the next Sir Isaac Newton or Albert Einstein? Learn from the master. Refat Bari. Watch his videos to achieve your dream.
Alright folks, let's stop clapping now. Welcome to lecture number 15 of special relativity. There we have our student right there. Right. And today we're going to find out how to get the net amount of enclosed charges from electric flux. Or something like that. Okay, so here's today's problem. Okay, you have a spherical kind of surface and it has a line, kind of wire passing through it. I used to have a sphere somewhere around here, but I don't find it anymore. Anyway, there's a wire passing through my sphere, and that wire has a linear charge density of 10 to the negative 12 coulombs per meter. Okay, make sure that makes sense to you. If it doesn't, hark back to lecture number 12 where we explain all of that. And the electric flux through this sphere is already given as 1.13 times 10 to the negative 3 voltmeters. Okay, so right here you can see that the flux coming out is going to look something like that, right? Who agrees with me that the flux look like that? Raise your hand if you agree, class.
I'm raising my hand.
Okay, that's how our flux looks like, and we're given that our flux is 1.13 times 10 to the negative 3 voltmeters. So, what is the question here? The question is, this sphere obviously has some radius, right? Do you agree that it has some radius? Okay, and basically we have to find what this radius is. Okay, from the given information, go ahead and find the radius of the sphere. Okay, I'll give you a few seconds, and good luck. Okay, in the meantime, let me just bring some water. Audience, you want some water?
I think.
Good. Make sure you stay hydrated, folks. Okay? So, hopefully that was enough time. Let's go ahead and find the radius of this sphere. What can I do and what will I do? Well, first things first, let me go ahead and write down Gauss's law of electric fields. Let's make sure that the audience can actually see what's happening on our screen right here. Let's see. Yes, they can, but hopefully we can bring it down a tad bit. And there we go. So what does Gauss's law of electric fields tell us? Well, it tells us that the net amount of electric flux is going to be given by the following formula. The closed surface integral of the electric field dotted with our normal vector times dA is going to equal my enclosed charges over the permittivity of free space. Okay? That right there is Gauss's law of electric fields. How can I use that in any meaningful way here? Let's see, what am I given? I'm given my total linear charge density, and I know that the length of this line is going to be given by twice the radius of the sphere. So I can just go ahead and use the right hand side of Gauss's law, right? So let's see if I can go ahead and do that in any meaningful extent. So I know my net amount of enclosed charges is going to be given by my charge density. Where's my charge density times 2 times the radius of the sphere. Why 2 times the radius? Well, because if you take a look at this diagram, the length of this wire is simply the whole diameter, and we know the diameter is given by 2 times the radius. Okay, and of course all of this is going to be divided by the permittivity of free space, a constant which we know already, right? Or you can look it up if you don't know. Okay.
I can look this up.
Right. And of course all of this is equal to the net electric flux. Right? But we're given the net electric flux. We actually know that it's 1.13 times 10 to the negative 3 voltmeters. So let's go ahead and plug in, shall we? So let me show all my work over here. So I'm going to have 1.13 times 10 to the negative 3. Okay, and what can I do to isolate my radius? Well, let me actually forego plugging in for now. To isolate my radius, I'm going to multiply electric permittivity on both sides, and let's see what I get. So let's come over here and I'm going to get my electric permittivity times my net electric flux is going to be equal to 2 times the radius times lambda, my linear charge density. And of course I'm only interested in my radius, so my radius is going to be given by my electric flux times my permittivity of free space divided by 2 times my linear charge density, and all of that is just going to give me my radius. Okay, so now we can finally plug in, folks. Now we can finally plug in. Okay, so we know my electric flux is simply 1.13 times 10 to the negative 3 volts meters. So let's forego these arrows a tad bit right here. So 1.13 times 10 to the negative 3 volts meters, right? And that's going to be multiplied by my electric permittivity, the permittivity of free space, which is simply going to be what? 8.55 times 10 to the negative 12. 8.55 times 10 to the negative 12. 10 to the negative 12 what? Coulombs over volts meters. Okay, so hopefully you don't forget that. Coulombs over volts meters. Let's free up some space this way. Coulombs over volts meters. Sorry if the board is starting to look messy, but we're almost there.
Not messy at all. It's actually pretty clear.
Thank you. And of course we're going to divide this by 2 times the linear charge density. And what is that? That's going to be 2 times 10 to the negative 12. And what are the units? Coulombs over meters, coulombs per meters. And all of that is going to give me my radius. Okay? So, first things first, let me do the easiest thing. Let's free up some space on the top. And so we can simplify this. This is just busy work really at this point. Because the rest is really easy. It should be really easy.
It
So,
should be a piece of cake, you're saying?
yeah. So we just have to simplify this little algebraic expression here. First, let's do some dimensional analysis and only hope that we end up with the right units. Voltmeters cancels out. Coulombs cancels out. We're left with meters, as should be. Dimensional analysis checks out. Now let's do the actual computation. Okay, so we're going to have that the radius of the sphere is going to be equal to 1.13 times 8.5 divided by 2, and then I'm going to put in all my exponents. So multiplied by 10 to the negative 3 minus 12 plus 12. And that's going to be in meters, and that's going to equal the radius of my sphere. So take some time to digest that. Pause, rewind if you don't agree with me at any point, or let me know in the comments if I made any mistakes. Anyway.
People probably won't be bright enough to catch them.
Right. So let's simplify this one first and foremost. Negative 12 and 12 will just give me 0. And our audience, can you please calculate for us what 1.13 times 8.5 is?
Okay. 1.13 times 8.5 is 9.605
And
divided by 2
yeah.
is 4.8.
Oh, thank you very much. So
02.
4 point what?
4.802.
Okay, so I'll just take 2 suffix. So I'm gonna write 4.8 times 10 to the negative 3, and of course my unit is meters, folks. And that right there is our answer. Why don't we feel proud enough to box it in, or confident enough to box it in? All right. So hopefully you understood what I just did. If not, you can go ahead and comment down below or email us at barrysciencelab.
Wait, what?
And we'll assist you with any problems you have. So thank you for watching, and we'll see you next time.
Subscribe to Bari Science Lab to fall in love with math and science, especially programming.